Okay, so well, first of all, thanks for the invitation to speak here. What I'm going to describe first is joint work with Jeremy Quastel and Janosch Ortmann, who's a postdoc of Jeremy. And I want to start just by reminding everybody, or those of you who may have not seen it, about the definition and what a big Okay, so I'm going to be interested in the asymmetric simple exclusion process. And just a quick picture about it. So we have particles in Z. We're only going to work in one dimension. And particles jump to the left at rate Q, to the right at rate P. We assume P plus Q equals 1. So there's that normalization. And, well, they just perform independent walks, except that there's this exclusion rule which tells that a particle cannot jump onto an occupied site. So every particle performs an independent jump unless there's a particle which precludes it. And really what we are going to be looking at, since we're interested in random growth in this case, is the height function. So how is the height function defined? Well, I just above every particle I draw a line of slope 1. And when there's a hole, I draw a line of slope -1. I put them together and I get this height function. Of course, and this is unique up to some spatial shift. And this is what's going to interest us. So we're going to study this height function. So this is what happens. So when a particle jumps to the left, say, this local minimum here is going to turn into a local maximum. Right? A particle jumping just changes this local minimum to a local maximum.
So that's going to be strictly one dimension.
Yeah, this is only in one dimension. Of course, one can define the asymmetric exclusion process in every dimension, but not the height function, not in this way. Okay, so and I'm gonna, one can make a choice here. There's a symmetry, so I'll say that Q is bigger than P, which means that particle wants to move a little bit more to the left, and thus the interface is growing up, so it's going upwards. And if one takes the case P equals 0, Q equals 1, this is a totally symmetric exclusion process. And what happens here, well, particles can only jump on one direction, and this is equivalent to last passage percolation, which is also the sort of zero temperature limit of polymers. But I'm going to be interested in the asymmetric case, not the totally symmetric case. Now, before going into that, there's 3 initial conditions which people like to look at because they're special for this model. The first one is the step initial condition. And here what one does is you put particles on every positive site. And then initially the height function looks like this, because these are all occupied, so they're all 1, and these they're all unoccupied, so it's slope -1, so it's basically, it's just the absolute value function. The next one is the flat initial condition. And here I put 1 particle every 2. And so this is called flat because if I look from far away, this looks flat. I just have this periodic initial condition, and I have this sawtooth type initial condition. And the other important initial condition is the stationary or Bernoulli initial condition, where I use a product measure down here. So I put a particle with some probability in each site, and then what I see here is a random walk path, basically, because I can either go up or down. It can be symmetric or maybe not, but that's what I see. These are important because they have some scale invariance built into them, and what that means is that, that's what the next slide, well, first of all, maybe I should say, besides these 3 cases, there are 3 mixed cases where I put one of these choices in one side of the origin and the other one on the other side of the origin, and those also satisfy the same sort of scaling invariance. And the important thing is that for the totally symmetric case, which is the same thing as last passage percolation, these 6 cases can be completely analyzed. So there are exact formulas which are based on some determinant structure of this model, which only works for the totally symmetric case, and one can compute everything. And this was a successful program by a long list of people, where everything has been, well, not everything, but things people are interested in can be computed. So an important example is what happens with the one-point distributions. So this is in the curved case, or the step case. If one looks at the height function, subtracts its mean at time t, which is a half t. I'm looking at the height function at 0. So the law of large numbers here is a half t, and I divide by t to the 1/3. Then this rescaled quantity converges to the Tracy-Winham GUE distribution. And so, well, the important thing here is that then the fluctuations are out of order t to the 1/3. And we see GUE. This t to the 1/3, of course, is supposed to be universal, but the exact statistics are not necessarily universal. They depend on the initial condition. So for the flat case, which is when we have this periodic sawtooth type initial condition, the same quantity now converges to the GOE distribution instead of the GUE distribution.
I'm sorry. What is 2R or 2
Well, that's just a normalization issue.
Hmm?
It's just a normalization. So here I'm defining the. You were asking about that?
Or the one on top? I just,
The 2 to the 1/3?
yeah.
It's just that I don't get exactly the GUE in the way it's classically defined. I get this scaled version of GUE. This is the distribution function of GUE, so if I scale it by something, it's still.
Just for the.
Yeah.
The
So it.
for the points.
Exactly.
Values.
Yeah. So it means that instead of getting the GUE random variable, I'm getting maybe 2 to the minus a third times that variable. That's all. It's just a matter of the scaling one chooses.
Just scaling of the density.
Yeah. Yeah. Okay, and well, in this case, so these distribution functions are given in terms of Fredholm determinants. That's one of the ways in which one can express this. And this is not so surprising, at least in this case, because the way these are obtained, these limits are obtained, come from the determinantal structure of the model. So there's determinants built into the method. And these exact computations, when people take limits, they yield certain series which turn into Fredholm determinants. So the fact that there's a determinantal structure here yields these Fredholm determinant objects. Maybe one thing, though I won't talk about it, is that in the case of ASEP, one can also study the multipoint distributions. So I can ask what happens with this height function at different points, and it's also well known what happens, and what one gets is the Airy processes. So maybe a picture here is, this is a picture of the exclusion process, started with the step initial condition, and what one sees at a later time, well, basically the law of large numbers is this parabola, and this is the height function, and the difference between the height function and this parabola, which is what we're interested in, after subtracting the mean behavior, that's what's called the Airy process. So this would be an approximate Airy 2 process. And the height at each point, that difference, that's what's approximately GUE. And it's true at every point. So if I look along this parabola, that's GUE. And the same picture holds for the flat initial condition. So now I start one particle in each, every 2. And the mean behavior gives me this line, which is growing in time. And now if I look at the difference between the height function and this line, what I see is the Airy 1 process, which at every point gives me GOE. So the totally asymmetric case is nice because there's this determinantal structure which makes computations not easy, but possible. Okay, so we're really interested in what happens in the partially asymmetric case. So now I just take Q larger than or equal to B, not necessarily with Q not necessarily being 1. And one expects by the conjecture of the universality in the KPZ universality class that the same fluctuations should arise, no matter whether Q is 1 or is not 1. So in the partially symmetric case, one should see, and that's what people believe, exactly the same fluctuations. Now, the problem is that as I said, when we go away from the totally symmetric case, it's not a determinantal process anymore. So we don't have the correlation functions are not nicely written in terms of determinants, and that's something that was it's very useful when one wants to take the limit. So that's lost, and one can think of this, if we want to think in terms of polymers, This is like a positive temperature version of the, so the asymmetry, the fact that now the asymmetry is not 0, one can think of it as this being a sort of positive temperature model. So there's one case which was the first one to be understood, and this is the most well understood to date, and that's the case of step initial condition. So in the case of step initial condition, Tracy and Wyndham got about 5 or 6 years ago a formula like this for the distribution of the height function. So really what they, so this, the way this formula works, I have a Fredholm determinant here of a certain kernel, which is given down here, and it's integrated over some contour. Now the way they, there's two things to note about this formula. First, the way they got it was by, they started with the dynamics of ASEP, and they solved the forward equation, basically, by using ideas coming from the Bethe ansatz. So there's a certain way to try to guess what these solutions should be, and they guess, and then they check, and well, they got the solution. And that gives a large formula with lots of contour integrals. And then after a long series of simplifications, they managed to turn that formula into something which has a Fredholm determinant in it. So this is just by explicitly solving the equation. But the second thing is that the formula they got written like this is still not good for asymptotics. So one would like now to take t to infinity in the right scaling and try to see GUE. And the formula one gets from this method is not good for that. And they had to post-process very heavily in very non-trivial and very specific ways this formula, so that it could be turned into something on which you can do asymptotics. So it's difficult to see it in the way I wrote it because it's not the point of the talk, but there's really something very non-trivial going in their computations where they basically have to factor out something from the determinant to cancel something out so that things end up in the right place, and then you can take the limits. So
What's X and Y there?
So X, yeah. So yeah, it's the position, and Y is just I'm asking. So this is the probability that the height function at this time at position X is larger than Y.
Here is Y. Y is contained in
Y is contained there. Yeah. Yes. So the problem is that this exponent, well, in principle, it doesn't look especially bad, but it's not good for asymptotics. If one try to, the one that ends up being good is not maybe so different. But if one starts trying to do critical point analysis on the exponent that appears here, this C appears there. So it just doesn't work. It's not, you just don't see what you need to do. And then they manage to sort of post-process this formula into a way in which the critical, this is the good, yeah, that's the problem. I was, yeah, so I was suspecting that as I was looking, because the problem is that the bad one has this Y appearing here. So I apologize for that, but well, this is what you get after a lot of post-processing. The earlier one doesn't look very different from this. So it looks sort of the same, but the problem is that the Y is not in the right place, and you can't see it. And then after lots of post-processing, they got this one. Okay, so thanks for the. Anyway, the point is that it's very specific to the step initial condition where they can perform all these. And in this case, they could get the GUE asymptotics. Now, actually, the same method works for the step Bernoulli case. So this is when you start with a product measure on the positive integers and everything empty on the negative integers. And in that case, the same method, so they were able to again solve the forward equation, turn it into a formula with a Fredholm determinant, post-process it, and finally take a limit, and they got the conjectured fluctuations, which I didn't put in the slides, but this can be done. So at least in the ASEP case and in the half stationary case, there's ways to treat this problem in this way. But, and this is what I want to talk about, the flat case remains completely unclear. So there's something about the flat case which is not, which doesn't want you to be okay, maybe I should explain first what's known. So there's two related works in the flat case. One is for the ASEP itself, and in that case, there's a result by Johan Lee, who was a student of Trek Tracy, and he gives a formula which is sort of the precursor of this one. So he gives a formula which is a certain series with lots of contour integrals, but which is not a Fredholm determinant. So there doesn't seem to be a way of turning it into a Fredholm determinant. So you can do the same thing. You can solve the forward equation and then, well, look at the right initial condition, do some combinatorics and get some formula. I'm gonna, so it will appear in a later slide. But the problem with that formula is that you can't do asymptotics with it. There's just, not even formally. It's very far from something where you know what's the critical points analysis that you have to do. It's just pretty much unmanageable. There's a related work, this is more recent, on the KPZ case. And this is by Calabrese and Ledusal, two physicists. And, well, this is a completely non-rigorous derivation. And what they do, I want to describe it very briefly because it's sort of related to what I'm going to say later. So here what one does is the following. I take the KPZ equation. So this is the KPZ equation. This is white noise. This is the one that I think.
I just have a quick question. Before you address whether it's a GOE, which is what you're supposed to get.
Yes.
But do you know the scaling is correct? The 1/3 scaling is correct? Do you have upper and lower bounds of the type that you have with a 1/3 scale?
As far as I know, I think the answer is no. But that's for, well, but that's for, but that's for KPZ already, not for ASEP. So for ASEP, as far as I know, the only cases where it's known is, well, it's the step case and the half stationary case, and it's also known in the full stationary case, and that's a result of Jeremy and Martin Balázs and Timo Seppäläinen. But there, it's not an exact computation.
The was the one that was just the particle at every other site, right?
Yes.
So that the scaling there.
No, I.
And in the case of the Poisson initial condition, that's okay or not? You don't know those features.
That's so.
I mean, I'm just after crude information now. Not
yeah. So.
That's fine.
This, no, but that's only in TASEP, I think. Oh, well, okay. So Poisson is like stationary. So yeah. Yeah, stationary case is better because of the stationarity, and you can attack it by some other means.
Oh, because it is
So
stationary.
Poisson is Bernoulli?
Yeah. So Poisson would be basically geometric gaps. So that corresponds to the stationary case. So that case is known in this case. Okay. So now one of the reasons people are interested in the asymmetric exclusion process is that, at least in this business, is that it approximates the solution of the KPZ equation. So there's a certain limit one can take, which is the weakly symmetric limit, which takes the height function to the solution of this equation. And here this is white noise. This is a very ill-posed equation, but I'm not going to talk about that, because here what one can do is formally take e to the h and get some z, and this z is just a solution of the stochastic heat equation, which is well posed and has no problems. Now, what I am interested about is the following fact. If I take this z, which satisfies some stochastic PD, it's just the stochastic heat equation, then this function, if I look at the moments of this z, and I call that function u, then this function satisfies this equation. This is not exactly well posed. There's a delta function here, but one can make sense of this. So this is called the attractive delta Bosegas. And it's basically I have a Laplacian, and then I have this interaction term here. Yes. Yeah. Yeah. So exactly. So what people do in the physics literature is that, well, one can find the explicit eigenfunctions and eigenvalues of this operator, and then one can use that to solve the equation, to give formulas for this quantity. And that can be done rigorously. Now, they use something they call the replica method. So the replica method comes from just the fact that there's a product here and one is replicating and then expressing this in terms of the solutions of that. But the problem is that what they want to do is they want to take a certain limit, or let's say, to put it a different way, they want to characterize the distribution of this z by computing this moment generating function. So they compute the moment generating function, and they take the expectation inside, and they get this quantity here. The big problem is that this is completely nonsense, because the expectation of z to the n, one can check, even from the formulas that one gets, that it grows like e to the n cubed. So this is wildly not summable, and the distribution is not determined by the moments. There's just nothing one can do. One gets to this point, and that's the end of the story. Of course, what they do is they keep going, and what they try to do is they, well, try to sum the series in a certain way which makes some sense, and, well, there's a trick which happens to work in the sense that it gives the right answer. So what they do is that they linearize this e to the n cubed using this formula, which is a correct formula. So this is the Laplace transform, if you want, of the area function. That's e to the n cubed. That linearizes the problem. They plug that in here. Then they're able to sum in n, because that's just a linear thing. And they get some answer. And they're confident that this is correct because they get the right answer. But there's, of course, no justification for it. So for instance, one thing you can do with this trick is you can try to sum this series, which is, of course, completely divergent. It makes no sense. And if one uses this trick, one gets this formula, which is, well, a reasonable formula. It happens to be the case that it gives them the right answer, but, of course, only in the cases where they know the answer. So that's what they do. But it's not something that's really available to do anything with it at the math level, except, well, try to work it out somehow in a microscopic setting where the moments are not so bad, and then try to take limits. So that's the idea. Okay, so that was, in a way, the introduction. And I want to describe the results that we have got with Jeremy and Janosch. So just as an overview, what we're going to get is exact formulas for certain observables in the half-flat and flat ASEP, so for moments. In the flat case, if one sums it in a certain way, a Fredholm Pfaffian appears. Instead of getting a Fredholm determinant, it happens that in the flat case there's a Fredholm Pfaffian. And these formulas we get are suitable in principle for asymptotics. So what I mean by that is that the critical point analysis works. The formulas are written in such a way where you can take limits, or you would think that you can take limits, but there's some technical problems which are still, well, we haven't been able to solve yet. But this formal critical point analysis, just sort of sweeping aside these technical problems, give the right asymptotics. So we get DOE, and we also get what we're supposed to get in the half-flat case. So I'll start focusing on the half-flat case first. So the way we do this is by using something that's analog to these delta Bose gas equations. So there's a work by Sasamoto and Imamura, and then later sort of redone in a slightly different way by Borodin, Corwin, and Sasamoto, where this is very analog to delta Bose gas case. So this is this is ASEP with any initial configuration which has a leftmost particle. So it's sort of it doesn't have infinitely many particles to the left. And I look at this quantity. So these are just the occupation variables, and this is counting how many particles there are to the left of this site. It's a certain observable. The important thing is that this is basically equivalent to the height function. So there's a way of turning the height function, a very simple formula turning this into the height function. So this is giving us information about the height function. And what they showed is that this function u can be characterized as the unique solution to this equation. So what this equation is, it's not so difficult to see what it means. This is basically something like the forward equations for the this is encoding the dynamics without putting any restriction on the exclusion. Yes. So it is just the occupation variable. These are the particles. So it's sort of mixing two.
What's tau?
Tau is P over Q. Where? Oh yeah, I forgot. I think I put it in an earlier slide. So it's measuring the asymmetry. But it's fixed. And it's not, I mean, it's a number strictly between 0 and 1. So this is encoding the dynamics without taking care of the exclusion. And this is a sort of boundary condition which is saying that, well, if I have a particle which is strictly to the left of the other particle, then there's something that cannot happen because no jumps are allowed. And that's being encoded by this equation here. And finally, the third equation is the initial condition. So the initial condition should be satisfied, though we only ask it to be satisfied for ordered sets of locations. So if we want to, here's a possible way of trying to attack the problem. If we want to solve look at the half-flat case, well, half-flat case has a leftmost particle, of course. So I can try to solve this equation. And that's what we need to do. So let me tell you a little bit, just a little comment before showing you the solution of the equation. So first of all, we're going to solve the problem in terms of certain contour integral formulas. And these are similar to things that Alexei Bordin and Ivan Corwin got for the Q-Whittaker process, or essentially for the Q-Tasep process, which is a slightly different version of Tasep, but with an asymmetry in it. So for that case, starting from this theory, which is the theory of McDonald's process, they can find contour integrals which encode things which are similar, they're completely analogous to this. And on the other hand, they can take limits of those formulas. And by taking limits of those formulas, since this process, the Q-Tasep process, is going to, under some scaling, is going to converge to the KPZ equation, the formulas they get converge to the solution of the delta Bosegraph, which is what I said is encoding the KPZ equation. But this only works in this case for the case of step initial condition in Q-Tasep, which corresponds to running the KPZ equation with delta initial condition. And what they recover are formulas which were sort of known, and they come from Heckman and Obdam in the late 90s. So they, in a completely different language, they had formulas which looked like this, and they seem to arise from these Q-Tasep formulas. And now, so this is an earlier work, but now looking at these equations that one has to try to solve, basically by analogy with the solution of this problem and the solution of the Q-Tasep problem, and also by using things which you can start, so by looking at Tracy and Winham's formulas, you can try to start guessing what are the objects that should appear. They could solve ASEP, so solve the set of equations for the case of step initial condition. So when you start with all particles with all positive sites occupied and everything else empty.
They just guess this formula and plug it, and then it's going.
It's something like that. So it's an educated ansatz, of course, but so it comes from looking at these formulas, looking at those formulas, and also looking at the Tracy and Winham's formulas to see what are the right exponents and stuff like that. I'm going to explain where this comes from. So
This formula is really special for 0, 1, 0, 1.
So this formula is for step.
Yeah.
This is, sorry.
You need density 1 half.
No. This is this. So this is density 1 on the positive integers. They can also do. So when I say they can also, in the same paper they get formulas for the half stationary case with any density. So this is the density 1 case, and it works for any density, but half stationary. But so,
But it has to be stationary.
they only got formulas for stationary. I'll show you that it doesn't have to be stationary. Half flat also, there's a way to solve half flat. In general, we don't know. So, but at least this one seems to be special, and we can solve it. So, but the point is that these two initial conditions fit with what was known from some other works, from the Tracy and Winham's works. The one thing I want to note is that even though this it's natural that how these started evolving from what they had done in McDonald's processes, and then how you apply it to delta Bosa gas, and then there's formulas for ASEP. ASEP does not fit into the McDonald theory. So the McDonald processes are a very general class of processes which have a couple of parameters, and they can be degenerated into lots of different things, but not ASEP, or not as far as anybody knows. But I think people are roughly convinced that it's not possible. So ASEP is something different. Yet this way of solving it seems to also match with what you can do in the Q-ASEP case, which is one of the sort of basic particle systems that belong to the McDonald processes hierarchy. So how did we solve this? Well, first of all, one has to check what's this U0 in the half-flat case, but that's just a computation, and it turns out that it's this initial condition. So I'm trying to solve the equations with that initial condition. That's my U at time 0. And the way we solved it is, well, by basically, again, it's a guess. So we had to guess and then check. And the guess was based on, again, on formulas like this, and also on the formula that Johann Lie had got for the half-flat case. So this is a formula for something different, but it sort of has some structure. And if you try to study what's going on with this formula, then you can try to come up with a guess.
This is your initial condition for your delta Bosa gas heat evolution, right?
So this is the half-flat ASEP initial condition, which is 1 particle every 2. And in the delta Bosa gas case, it just corresponds to solving with 1 on the positive reals and 0 on the negative reals. That's the initial condition we're considering. Okay, but when you go back to so one thing is the initial condition for the particle system itself, and the other one is the initial condition for this object.
Yeah. Oh, but you still have the same delta Bosa gas, right? No. I'm calling delta Bosa gas along with delta function interaction.
Yeah. So these. So okay, I'm not sure if I understand the question, but you can take a limit of these dynamics to the delta Bosa gas dynamics, and well, the initial condition is going to converge to something. The one we're considering here converges to the initial condition, which is basically the indicator function of x being positive. So it's 0 and then 1. Okay, so. I won't get into this formula, but this is a formula that Lie had got for the probability distribution. It's not what we're looking for, but it sort of has things one can use to get some inspiration. So these are the equations again, and this is the solution. And I want to take a couple of minutes just to show you how this thing works, because at least we seem to think that it's remarkable that it works. There's something sort of miraculous that happens, and the point is that it doesn't seem to happen for other models. So there's something about ASEP which makes this possible. So the idea is the following: I have to solve these 3 equations, and this structure here of having these double products ZA ZB over ZA minus tau ZB it's sort of what we get from the solution in easier cases. And the important thing is that there's a certain boundary condition, and I have to find something that's going to satisfy the boundary condition. So given that I have this object here, one can check that the one thing that works and it's going to satisfy this boundary condition is to have this product here. And it's pretty much fixed. And the reason, I'm not going to do the computation, but the reason is basically that when you write down the answer of this left-hand side, basically what happens, well, there's a certain difference that one has to compute, and what you get is something like ZA minus tau ZB. There's that with B equals A plus 1. So I basically get ZA minus tau ZA plus 1 on the top. And that will imply that everything is 0 simply because it's going to cancel one of these terms here. So I'm going to get something like ZA minus ZB. And all the contours are the same, and everything else is symmetric. So since everything else is symmetric, and I have this anti-symmetric thing there, that just makes the integral 0. Because I'm integrating, I have a double integral over an anti-symmetric thing, it has to be 0. So that tells you exactly what this factor has to be. So you're forced to putting this factor here or something which is roughly equivalent to that. And then, well, the only thing that depends on x is this factor. So now if I want to solve this equation, it's pretty easy. I just have to put this exponential there, which is exactly the thing that's going to throw down what I need to satisfy this equation. So this idea works always to satisfy 1 and 2. But now I need to solve my initial condition. So that's the question. What should I do to get the right initial condition? And the idea is the following. The idea is that I need to, so the important objects here are going to be this and that, well, and that as well. I introduce a pole somewhere, which is such that the residues at this pole, when I compute, they give me the initial condition I'm looking for. So this guy introduces two poles, one at tau to the minus a half, and the other one at minus tau to the minus a half. And one can check that, well, when I plug in the one with the tau to the minus a half, I get something here, which looks like tau to the half xa. And when I plug in the other one, I get something, so essentially I get, I hope you can see, but essentially one gets something like tau to the half x a times 1 plus minus 1 to the xa. Just because when you plug in the one that has a plus, it always gives you a 1, but when you plug in the one with a minus, it gives you the thing that's being raised to the power of xa has a minus 1 in it. And this is where the periodic initial condition comes from, because this is only 0 when this is only, well, there's a half somewhere. But this is essentially 1 when xa is even and 0 when xa is odd. Now, well, that's the idea, but there's a big problem, because, of course, when I compute the residue here, well, t equals 0, so this is gone. But when I compute the residue here, I'm going to start adding some more things over there. So that's a problem. And then what you have to do is you have to multiply by something, which turns out to be this thing, which is exactly going to cancel whatever you get from this guy. So, okay, you go ahead and you multiply by that. But now you have a further problem, because when I multiply by this, now I introduce more poles. This guy has some other poles, which I'm going to see. And there's no reason to believe in principle that these poles are not going to contribute. So in principle, you try to do this, and then you find, okay, I start putting all the pieces together, and it doesn't fit. And it just happens that for this case, all the poles that I get from this guy get canceled in a sort of magical way. So basically, what happens is that there's a pole at 1 here, and when I evaluate at the residues coming from this guy, I don't have time to do it in detail, but basically the pole that you get from this guy plays exactly right with that guy, and the pole that used to be at 1 disappears, and essentially what that does is it tells you that the pole there, it's removable, and nothing happened.
Okay, so you use this method to fix the initial states. Can you tell us how general use these methods?
Okay, so the answer is,
For the initial states.
yeah, the answer is, I think they're not very general. So that's the problem. So there's there's
My feeling is kind of like it depends on this even nuts. How about let's say 2 zeros?
no. So in that case, we don't know how to do it. So that's okay. So there's these three classes of initial conditions that I described at the beginning. Two of them are already solved, and people believe, just part of the sort of KPZ universality class, that this should be solvable. So one should be able to write. That's not a very concrete conjecture, but supposedly one should be able to write formulas. So it turns out that in this case we can do it, but it's clear that if I want to do something different, just when one tries to start doing this, it just doesn't work. And for instance, if I took one particle every 3, as you said, that's also supposed to be GOE because it's flat again, only with some slope, but it should give me the same answer. But in that case, we don't know of any way of solving it. This just happens to work for this case.
But shouldn't there be a general argument that if you let the evolution act on your initial condition for a relatively large time, then many different initial conditions will lead to the same types of interfacial fluctuations?
Yes. I mean, yes, that's the belief, but we're far from being so supposedly.
So you can only do your problem if you have exact solutions.
No, there's certain classes of, if I understood the question correctly, there's certain classes of initial conditions which all go to the same, which will have the same asymptotics.
Yes.
So when I choose the step initial condition written as I wrote it,
They say you take step or you take flight, they convert because of different objects.
yeah, but
No,
so
no, but I mean, you see flat,
Small perturbation.
yes,
Yeah,
small
so-
perturbations, you have some kind of basins of attraction that
yes, but we're far from being able to prove something like that, and in very specific cases we can show the convergence. And of course, one would like to show that this holds in more generality. It's
so that shows that that's the usual problem with exact solutions, right? One feels one doesn't really understand anything except some very, very special object.
well, it's
He's underdoing it. It's not. It's only this initial data, only this model.
so
So what if you have flat whatsoever? One of the particles is in the wrong spot. Like if
Presumably,
your flat grabs one of the particles away, it still doesn't work.
so that's okay.
Yeah, exactly.
No,
Just
they
do the
can't.
smallest perturbation.
No, they can't.
So-
The formula won't work.
So the interesting thing going on here, at least one aspect of it, is that even though people believe that there's these general classes of initial data which should go to somewhere,
Yes.
even in the simple cases, so even for ASEP, which is supposed to be easy, or not easy, but easier at least, there's only, so if I want to do flat, I can only do certain flat, and I can't show that the rest, the flattish things still have the same. It's only for the one that I can do.
What about local, if the perturbation is local again? You
It's
can't-
not known. Well, maybe now for ASEP, there could be a way of doing it, but it's not known, and in these cases, there's just nothing. So, but the interesting thing is that there's these three worlds of initial conditions: flat, step, and stationary. For step and stationary, there sort of seems to be something going on where you can, well, solve it for ASEP, and you can solve it for Qt ASEP, and you can also solve it for the delta Bose gas. But for ASEP, this is the only one known. And there are, so for Qt ASEP, which is sort of the analog of ASEP, but the one that corresponds to the McDonald's world, there is an analog of these equations, or maybe these ones. One can write them, so they also wrote them in the same paper. But they can't be solved. Or you try to do the same thing, and it doesn't work, and we're pretty sure that it really doesn't work. You get formulas like this, but instead of having these double products, when you look at the second moment, you get double products. But when you look at the third moment, you get triple products. And when you look at the fourth moment, you get quadruple products. And then it's sort of done. You can't do anything else.
So maybe one more question. I mean, obviously there are lots of miracles arriving in the analysis. Do they arise for similar reasons in these different cases, or the miracles arise for totally independent reasons? If you compare this miracle
So-
to the one in the body encoding McDonalds and so on.
So it's different sort of miracles. That's the problem. So this is a very specific miracle. They have a miracle, if one wants to call it, where all these things can be explained in terms of some big object, which are these McDonald processes, and those explain the formulas because they just come from Whittaker functions and stuff like that. Here we have to solve this, and so in the step case, which is this one, in a way it's not so miraculous. If I try to explain how this works, then okay, it's the boundary condition works in the same way, the dynamics work in the same way, and when you try to plug in the initial condition, it's sort of very easy. You have this pole at 1 and everything else is gone and nothing happens. So you don't need much going on. It just happens to work. Here there's a sort of, I mean, one has to go through the computation to see it, but there's several miracles going on so that everything fits together and it works. And it doesn't seem to work in other cases. It just doesn't. So in Qt-ASEP, this structure is not there. Or it's very hidden and we can't see it. But the obvious thing is just not there. Okay. So by the way, we can also, so in the half-flat case, one can use the same idea to solve the delta Bose-Gas. And when one solves the delta Bose-Gas, this is the formula we get. It can also be, one can also obtain it as a limit of the ASEP formulas. And after playing with them a little bit, one can get to the formulas that Ledusal and Calabrese had gotten for the delta Bose-Gas.
Which is semi-infinite conditions. Does one know what the stationary state is as t goes to infinity? Forgetting about the exact formula, it's just, is it a Bernoulli state or is it known?
Yeah.
It's known that it's
Yes.
Bernoulli?
Yeah.
And that comes from what? From where is that known?
So in the case of the particle system,
Yeah.
well, it's just that. Okay, but in the
It could be a superposition of Bernoulli, so things like that. Stationary
yes, of course, but in the semi-infinite case, well, no, it's just I think it's easy to check from the dynamics. It's not a hard computation.
I mean, there's some reference I'd like to see.
But this is I don't know where it's proved, but it's rather classic. Okay, so there's this work by Calabrese Ledusal where they get these formulas.
I apologize if I'm asking all these questions.
Okay.
You know, I'm not used to this kind of mathematics. This formula from the bottom
I'm not used to it.
doesn't tell me absolutely anything. I just don't see anything when I stare at this formula.
At this formula?
No, the other one. What can you do with such formula?
Okay, this formula. So this formula. This is the point. This formula is nonsense.
No, but even if it were meaningful, it's monstrous.
It is monstrous. So this formula, what it's doing is it's really not very beautiful, of course. that much I agree. So there's two things going on. First of all, it's sort of encode.
But if you do the Airy transform,
Sorry.
if you do the Airy transform, then this will become meaningful.
Yes. So if I do an Airy transform, this becomes meaningful. So if I take these e to the n cubes and I do that, it becomes meaningful. And if I wave my hands a little bit, I can take a limit and I can see the right asymptotics. So in that sense, it is meaningful. No, so the Airy, it's not, one doesn't compute the Airy transform. You just replace e to the n cube by this integral. So it's e to the n cubed equals integral area of x e to the n x.
You just exchange summation.
So I just does. So I do Fubini, but that's not allowed, of course, because this is divergent. But I do it, and now I have to sum in n, but I have something linear, so it gets much easier, and you can do it. Now there's
Your formula on the top is mathematical rigorous.
yes,
Then you say you can, after some process,
yeah.
you can get
So there's two things being mixed here. because I wanted to show this sum. So I start with this formula. This is a formula where the contours are all different. And if you want to do asymptotics, you would better have all the contours the same. So what you have to do is turn this into a formula where all the contours are the same. And as you do that, you're going to start crossing some poles, and that's where you get things like this.
So on the other hand, you cannot do
So
rigorous from the top.
yeah, so what you get out of that is basically one of the terms here. And then you sum it to get the, and that's rigorous. So we have moment formulas for the stochastic heat equation, which look like this, but without, but these sums here are not infinite. So it's fine. Now what they do is that they sum and then they keep going. Okay. Yeah, so this is what I was saying. It does not seem to work for anything else. Okay, I guess I'm running out of time. So I probably won't have time. I'll just show the formulas. Won't have time to get to the flat formulas. But anyway, so this is a little bit of what I was discussing. I have a certain formula for a certain object in ASEP, and then you have to do some tricks, and you can turn it. So this is, I would like a formula for this, and I have a formula for that. And all the x's are not allowed to be the same here. But there's some combinatorics which takes you into a formula like this, and we get a formula which looks like that. Okay, it's again, this is a formula which looks as bad as the one on the previous page, except that I cheated because I sort of took the definitions out, so now it doesn't look that bad. And these things here are the Q-Epoch-Hammer symbols, and one should think of them as some sort of Q deformation of the gamma functions. So these are very analog to the gamma functions appearing here. So the two formulas are quite analog. And in fact, one can take a limit formally if you want and see the other formula rising. Now, the nice thing about this formula is that this is a positive random variable because it's counting how many particles are to the left of something. So that's less than 1. So I'm allowed to try to form a generating function. So this is the analog of what happened in the delta Bose gas case. This subject is like e to the n q, and here it's just bounded by 1, so I can sum. And that's sort of the replacement. After the limit, it won't be true. But before the limit, this is less than 1, so what I can do is I can form a certain generating function, try to form the moment generating function. Instead of doing that, what one does is that it's basically, this is the same exponential, except that instead of dividing by k factorial, one divides by the q deformation of the k factorial, which is the number appearing there, except that q, so there's a problem here because classically these deformations have a q in them, but here q means something different. But in any case, what one does is that I divide by these m sub tau factorial and then sum and form a generating function, and you get a certain formula which looks like this. So this is just by summing the formula and by applying this trick, which is in a way it's the replacement of that trick. So all I'm doing here is I'm replacing these sums appearing there by certain integrals like that, which are encoding poles. And these poles are just giving me exactly the sum that I look for. So this is a way to, in a way, analytically continue this formula. And this allows, in the end, to write a generating function for all parameters here. The point of this is that this generating function here determines the distribution. So this is already a formula for the distribution of the half-flat case. And there's a way to take a limit using this trick. So this is just a basic identity. If I compute this limit for a certain random variable, it's the same as computing that limit. And well, it happens that I can replace the exp by this tau deformation of the exponential function, and it works. So one gets that by taking a limit of this formula, basically of the left-hand side, that gives me exactly, this is what I would be looking for in the half-flat case. So this is like the trace and Widom asymptotics that I showed you. It's the height function minus a certain thing divided by t to the 1/3, And this is exactly what I would like to compute. So this gives me access to the type of thing that I want. The only problem, so in fact, if I compute it, I get the right answer. And the right answer is that if I look at the height function at x, then what I should see is the marginals of something called the area 2-to-1 function, which is a certain process which interpolates between GUE and GOE. So since this is half flat, it's putting step on one side and flat on the other side. As you move x, you should interpolate between GUE and GOE. And that's what we see. The reason why this is not exactly, so everything works nicely, and the critical point analysis works, except that there's this new factor here, which we haven't seen before in any of the other cases. In all the other cases, you have determinants and then just diagonal products. But here you have a determinant, which is nice, one can easily control, but there's this double product. And this function alpha is not really very nicely controlled away from the critical point. So essentially, this is giving you, maybe it's bounded by 2, say, but it gives you something which is like 2 to the k squared, and we can't yet control that. So there's some work to be done, but apart from that, at least this shows the right asymptotics. Okay, since I'm running out of time, so this is the picture of the area 2-to-1 case. So this is exactly the shape that one sees, and this is interpolating, and that's exactly what we're seeing in the limit, maybe a little bit formally. Now, basically, to get the flat case, what one has to do is take a limit of the half-flat case. So I'm standing here, and now instead of looking at a fixed x, I looked at some x and take a limit as x goes to infinity. And I probe into the flat region to get a formula for the flat case. And that involves, well, looking at this formula, taking a limit, and there's a certain factor here which has to be controlled. So there's a certain contour deformation that you need to do, and there's a very, very big sum that appears, and one has to start doing lots of things. And the only point that I want to make in the time that I have is that, so let me just show the final formula looks like this. So I get a formula. I get a formula for the moments, which has a Pfaffian in it. A Pfaffian is a generalization of the determinant. And this involves lots and lots and lots and lots more miracles. Well, maybe not lots, but many other miracles, like the ones we were talking about. And they seem to be related with the miracles that we had in order to be able to solve this thing. So there's certain nice symmetries which produce gigantic cancellations, and they produce this Pfaffian for you. So in the end, we get a Pfaffian formula for the moments, and then one can see that I cannot exactly sum it because this is not bounded by 1. This is not bounded by 1 anymore. This is blowing up. So one has to pre-multiply by something, and then, well, there's a different exponential deformation that one can form. And in the end, one gets a formula like this with a Fredholm Pfaffian, which is the analog of a Fredholm determinant, and actually it can be written as the square root of a Fredholm determinant. So at least we can uncover this Fredholm Pfaffian or Fredholm determinant structure in the flat case. But here we're facing, and again, we can formally take limits and get GOE. But the difficulties are bigger in this case because there's a moment problem, so things are not nicely determined. But at least formally, well, we have this formula, and formally we can recover the right asymptotics. Okay, thanks for your attention.